Yeah, thanks, Lukas. We are the end-to-end multi-channel, multi-talker ASR team, and I'm going to explain briefly what we're doing, what we did in the 6 weeks, and we will do in the next months, I think, and maybe years even, because I've been working on this problem for 6 years, and many here have worked on this problem for, I don't know, half their lifetime, at least. So, yeah. We are 17 full members teams, 2 undergrads, 9 PhD students, 4 full-time senior, and 7 members that joined for a few weeks, like from Panot AI, Hervé, Antoine, and lately Shinji Watanabe, and Jan Profund has been also joining us in the lab, working with us. And this is a pic of our team, like working also outside the lab. So like Dominic on the bus and Matti Wisner while eating. Everybody who launch experiments at every time of the day. Jundu managed on the boat trip, so he is ahead. So what our focus is on conversational everyday speech. We want to tackle settings where you have multiple speakers, and we want to deal with overlapped speech and do speaker attribution together with recognition. And to do this, you have also to tackle scenarios where you have a formal or a more colloquial language. And colloquial language often comes with complex turn-taking dynamics, like you're talking with your friends, so you may have like back channels, a lot of overlapped speech, a lot of laugh, false stutterings, and so on. And these are very difficult to handle by the systems. And we will also deal with situations where you have lots of reverberation, like this room, for example, has quite some reverberation, or background noise or background music that can make the problem more difficult of recognizing and attributing the words. This is one example. So you see, there are many people talking at the same time, and this is like 4 people mostly, and the audio is quite clean, but you know, like they are interrupting each other and they are barging in and so on, and this breaks current system. So it requires some specialized techniques to handle. We are the multi-channel team, so we also another challenge we need to take care of is we may have different recording setups, and we want our system to handle multiple recording devices. So you can have like a linear array device or a Google Home device with a circular array, and also I don't know, like phones, for example, that have more exotic array configuration and so on. So most of the devices today, they come with multiple microphones. So if you can exploit multiple microphones, it's better, because you can do like better noise suppression, noise or speech separation. But sometimes you are left with a single microphone channel, because maybe the pre-processing was already done. And in some configuration, you may have even multiple devices you can use, like like a hybrid meeting we are accustomed to. Like everybody is sitting in the same room, everybody has Zoom on their laptop, and maybe everybody could use his own laptop to transcribe the speech together. And there are challenges, but also like a lot of opportunities. Of course, like our main focus is speaker attributed transcription. But like the problem is more general. If we can tackle multi-talker speech, we are also able to have like virtual agents, like multimodal LLMs that can interact with multiple people. This is not possible right now, but if we are able to tackle complex environment and doing recognizing multiple speaker speech, then I think it's possible to also port these techniques to multimodal LLMs, or even assistive technologies. Like many people work on speech separation in our team. So this is a very practical problem for hearing aids device, for example. So, but yeah, we work mainly on speech transcription, and our problem is basically having multiple microphones, one or n microphones. We want to do diarization and ASR and get speech recognition plus speaker attribution at each word and segmentation. And the system hypothesis should look basically like this. We will have end time, start time for each utterance, the words, and then the speaker that spoke that utterance. And you will have multiple utterances because we deal with long form audio. So we need to do also like the segmentation. And this is a brief, a brief to short tutorial so you won't get confused by my colleagues' metrics, because most people here, I think they are familiar with word rate, but we care about also segmentation and speaker attribution because we have long form data. So basically, our system hypothesis and time, start time, may not be aligned with the reference, and also the speaker labels might be different. So we need to score our system, so we're taking into account these differences. And we need to align the reference and the hypothesis to doing that. So there are multiple word rate flavors, pretty much, that can do this, and each flavor measures a different thing, like Orquare measures only the speech recognition, so only the words. And then you have like CP word rate, which measures speech recognition and speaker attribution. And TC-ORC word rate, which measures speech recognition and segmentation, but not speaker attribution. And finally, like the most used, I think, is TCP word rate, which measures everything. So it also measures for if the speaker has been incorrectly labeled and if the start time and time are wrong. Together with, of course, like the speech recognition. And the current state of the art, like Wave2Vec, Hubert, Whisper, they work beautifully on single speaker, single channel scenarios, and they may even surpass human performance on some narrow domains. But basically, when you turn to complex multi-talker speech, everyday speech, pretty much, they break completely. One reason is that they use word rate, and so they don't care about segmentation, and they use Oracle diarization and so on. But even if we use Oracle diarization and then we throw a state-of-the-art multi-channel speech separation, like GSS, Whisper performs very poorly. So you can have like 37 on some scenarios like Chime 6, 37 TCP word rate, which is too high. And so we need specialized techniques for this type of problem. You cannot just throw more data to a next token prediction model and it will solve it. So to also raise awareness about this problem, we just, during the workshop, in the first weeks, basically Alex, he did this benchmark. He put together this benchmark which is open to everybody. And actually, like NVIDIA already submitted a system, like the Parakit Plus Former, the last entry there. And in the last weeks, it has been populated, and we have some established state-of-the-art right now with the DCOW model and the target speaker Parakit version from Dominic, and who else? Shilu also contributed. You will see some of these works, like will be presented next. And yeah, it's open. It's right now you can submit your system. And the current state-of-the-art approaches for this particular problem, they rely on very complex pipelines. And the goal, one of our goals is like to make it simple. Like for example, in the not so far meeting challenge, the first one is the USTC NERC slip, which actually came to the workshop and contributed with us to try to improve on this. Is this system, for example, which is very complicated, like consists of deliberation, overlap speech detection, separation, diarization, and then another separation, and then diarization again, and then finally ASR. It works beautifully, like because like the TCP word rate was around 17%, so it starts to be usable, but it's very complicated. So one of our goals in this workshop was okay, like can we do maybe just diarization then separation, the ASR, much simpler pipeline, And so some of my teammates explored this direction. Other teammates like try to, like, okay, let's not do explicit separation. Let's take just diarization and condition with the diarization ASR system, and make it an even more simpler pipeline. And this is actually what my colleagues did also previously for the Not So Far challenge, and which was the BUT-JHU system, which achieved the 3rd place. And now it's even improved. Like Alex will show how he improved the numbers further during these weeks. And yeah, basically how you turn the single speaker ASR to target speaker multi-talker ASR, because this method was very effective and it's been a core component of also our work here together. So I think I leave the word to the expert, Alexander Pollock, about the DCAO system.
Thank you, Samuelle, for a very nice introduction. And I will now go through what our baseline is, what are the key components of it, and they will also reappear in some other extensions of our model. So, as Samuelle said, our system is based on ASR and diarization. So here you can see whisper and diarization. Output of diarization just tells us who speaks when, which we can have up to n outputs, which could be somehow problematic for the ASR to generalize if it doesn't see that many samples of 10 speakers, 15 speakers. So we propose a way how to make it speaker specific and agnostic to the number of speakers. So for this very reason, we have STNO mask, which is specific to speaker. So for this example here, we have 3 speakers, Mary, James, and Michael, and now we will construct STNO mask for speaker Mary. So STNO mask consists of 4 classes: silence, target speaker speaking, non-target speaker speaking, and overlap. So first, we've seen the target speaker. So this is just the probability that for each frame, target speaker is speaking. So we see right now it's 1 for first 3 frames. Then we have probability of silence. So for the last frame, it's silence. Then we have non-target probability. So Mary is not speaking and someone else is speaking. And overlap probability. So Mary is overlapping with someone else. So this is the STNO mask. And question now is how we can incorporate this STNO mask into the ASR model. So here on the picture, we use Whisper. This is like one of the state-of-the-art ASR models. And on the right side, we can see how it unrolled. So it's encoder-decoder model, which has n transformer layers, some convolution 1D feature extractor, and positional embeddings. So how we can insert this STNO mask into the Whisper to not break it? That's the question. So for this reason, we designed these FDDT layers, which are frame-level diarization dependent transformations, and we insert them into before every transformer layer in our Whisper encoder. And what this FDDT layer is doing is basically taking the sequence of frames, which is demonstrated by these pink or red vectors, and it transforms it or projects it to 4 different subspaces. So here we can see 4 transformations, each for S, T, N, and O. So 4 different transformations. We project our sequence of embedding. And now we have this STNO mask, which are the probabilities. Here it's binary, so basically it's just selection. And for each frame, we now select corresponding transformation. And then we convexly sum everything together. So given the red sequence of embeddings, at the end of this layer, we get this mixture of different colors. But if we do so, we break the model. So question is how we can do that to not break the model, to have the same flow in the model. So what we can do, we can initialize these layers to be identities. If we do so, the flow in the model keeps the same, nothing changes, and we can start training the model to learn how to rotate the space, where to project the embeddings, to make it as simple for the model to learn to separate speaker from the mixture. But how we can even help the model at the initialization is to initialize the S and O N projections to suppress whatever comes in. So in this example, we will basically suppress everything from the 5th up to nth frame. This is the STNO and FDET. It will be appearing again and again through our presentation. And if we add those things together and use the whisper, we got this diarization conditioned whisper. This is our baseline model. So we used it, we designed it for Not So Far challenge, then we scored it on other data sets, and we are basically on par with best models on both realistic data sets and also simulated data sets, which is this Libre2 mix. But what is even more cool about this system is that it also still works on single speaker data. So here in this table, you can see how it performs on LibreSpeech, Tedlium, and Vox Populi, which are standard single speaker data sets. But what is even better is that if we train our model like that, it remains the multilingual capabilities of the model. So if we just fine-tune these FDDT layers and whisper encoder, we can still decode multilingual data. So we demonstrated that on a few recent challenges. So we were awarded by the jury prize for Not So Far challenge, which Samuelle already mentioned, and we also secured 2nd place at recent multilingual conversation challenge. Now I will continue with extensions that we did during this workshop for the baseline system and how we improved it, what we did to make it even better. So we started with V1 version, which is the die code that I showed you, and now we have the version 3.2. So first thing is architectural-wise. Previously, we've seen these FDDT layers were added before each transformer layer, but if we do just this, we can break up the continuity in the positional embeddings. So we added one more layer, which is suppressively initialized before the positional embeddings. We use less strict suppressive initialization. So instead of pushing everything to 0, we use some scalar diagonal matrix with, let's say, 0.5. We also freeze the decoder to maintain the multilingual capabilities even better. And we re-implemented the whisper decoder, we enhanced it, and we added post-processing, which detects all the hallucinations. And finally, we also added some augmentation. So not only augmenting the speech waveform, we also augment the STNO masks to simulate the errors that our derealization system can do. So here you can see where we were before the workshop and where we are now. And basically, we even improved on AMI, Not So Far, and Libre2 mix. And on AMI and Libre2 mix, we have state-of-the-art results. So here we just played a bit with the architecture, did some tricks, trained it better, and we have even better numbers. Our model is now on Hugging Face. You can pretty much just with 3 lines of code get it and run it for yourself. It's already getting some attention, so you can see some downloads there. And it's possibly will be also added to the transformer libraries. So I showed you STNO masks. They are quite fine if there is not really much overlap. But let's imagine now we have this scenario where we have 3 input mixtures, just, 3 inputs without any overlap, just a single speaker speaking. And now we add them together. We just add the whole signal together, and we see that now we have a lot of overlap. And if we now extract the STNO masks for all the speakers, we can see that, for example, James and Michael has almost exactly the same STNO mask, even though their transcription, what they said, can be really, really different, which can make it very hard for the model to learn just from 2 embeddings that it should basically switch to the other speaker. So to fix this and maybe improve the model, we took advantage of the enrollments. So basically enrollment could be some speech where only our speaker of interest is speaking. But our framework also works if you just add there, like most of the time the target speaker is speaking, there it could be still a mixture of some other speaker already also being present. And now we add cross-attention. And the cross-attention can now take a look of how our target speaker is looking, what are his embeddings in the time, and pull this information into the original flow of the model. There's MLP layer, which basically makes those information. So, doing so, we can even further improve performance of our DICO V3 and get the results even lower and really achieve the state-of-the-art results. So, enrollments can even make the STNO like more informative. Next thing that we tried is, can we turn target speaker ASR into multi-talker ASR? Can we design some modules that will allow us to communicate between instances of target speaker ASR? Yes, we can. So for this very reason, we reused some existing modules like transform and average concatenate, cross-attention, co-attention, and propose a novel method which is called competitive cross-attention. Some of them will be covered later by Yoshiki in more detail. And basically, here we can see that with some methods, we get some improvement, with some not. So the outcomes here are quite mixed, but our new proposed method, competitive cross-attention, seems to work. And the difference here between the normal cross-attention and competitive cross-attention is that competitive cross-attention allows one instance to look only to the frames where the other instance is not looking. So basically there is competition between 2 branches where each of the branch can look. So it can fix some of the errors, but it can also introduce new errors. The other approach that we were working on is, can we do speaker identification and target speaker ASR in one model? Can we use that and maybe just rely on the short form diarization? So we did some preliminary experiments, and basically we can get to the accuracy of 0.5. So we can force the model to be aware of speaker identity, but we also lose some performance in target speaker ASR. So, but this could also simplify the whole framework, so we can only take embeddings of after the ASR and cluster only those. So this is one of the future approaches that we might investigate. And that's it. Thank you. And now I will pass to Jin.
Oh, I take the advantage because I'm close to the mic. So when you do the speaker embedding modification of decoder, do you need to hand specify the segments where you extract the embeddings, or can this be done somewhat automatically by clustering or just by some speaker distances? Or
so basically on the input here, it's still the input mixture, and we just add this STNO mask. And based on where we see that there is a target speaker speaking or there is an overlap, we use these embeddings and we use contrastive learning to force these embeddings to be different from the different speaker and same from the other mixture of that speaker where he's present.
Okay, okay, thank you.
Thank you.
Thanks, Alex, introduction. What I'm modifying is also is try to extend this DICO FDDT, this deterministic transformation, with Bayesian learning. Just a recap, in the left-hand side is the DICO, the framework. What I previously, the FDDT linear transformation, this is WS, WT, WN, and WO. These are linear transformation. Here, what I just modify is by substituting this linear transformation by using the FDDT Bayesian transformation. And so one question also comes up, where I have to substitute this deterministic transformation with Bayesian learning transformation. Here, I use neural architecture search to search for the optimal position to embed this Bayesian layer on the whisper encoder. The motivation behind this is Bayesian learning can model the uncertainty estimation. It provides the confidential levels for the predictions. This is crucial when the data is noisy or even limited. This helps the ASR system know how sure it is. The second is this is robust to the variability. It offers a principled way to integrate the various types of information, acoustic, speaker, and language, to overcome the noise and diverse speaker styles. Just is it naive, like Bayesian CM, when we take the prior and when we visualize the data, we compute the likelihood, then using this Bayesian CM, we compute the posterior distribution. Here is the results by using the Bayesian version of DICO, by substitute this FDDT linear transformation with Bayesian transformation. So we can see we train the model using the not so far, Libre2Mix, and ARMY. We combine them, and we test on the test set of those data set. In the last, we find the average score, combine those, we slightly have an improvement. And except also Xilo have some modification on the DICO. I will pass to him.
All right. Yeah, so previously Alex talked about DICO for general multi-talker scenarios. My work extends DICO into streamable multi-talker cases, such as live transcriptions or event detection for like voice assistants. So DICO and many other target speaker multi-talker ASR systems are not very suitable for streaming applications due to their runtimes. So in the case of DICO, the ASR system is run once per speaker, which could end up being very expensive. And there is also this diarization step where long-term diarization requires speaker ID and clustering, and these things are not very amenable to streaming situations. Additionally, some of the tasks I mentioned before, like with transcription, don't necessarily need speaker labels, or they could benefit from post-process speaker attribution. So the question becomes, can we trade speaker labels for better runtime? And so the idea is that we assume that there's only going to be a few chunks of more than 2 overlapping speakers in any given conversation. This way, we could create sort of 2 streams or masks of mostly non-overlapping speech, where both streams are speaker agnostic. That way, we run the ASR system through both streams, and that way we get the entire recording. So the way that we do this comes from an idea that originated in streaming source separation, called heuristic error assignment training, or HEAT. In HEAT, what you do is you take the heuristic of utterance start times, and you assign them to one of 2 channels. By default, it's assigned to the first channel, but in the case where an utterance is overlapping with something that's already in the first channel, then you assign it to the second channel. And once again, because it's speaker agnostic, the same speaker could appear in both streams. How this is done in practice is I take a diarization system, and I take the diarization labels produced from them, and I run HEAT assignments with those. So we create SDNO masks similar to how Alex previously explained, with silence, target, non-target, and overlap. And we run DICO in a very similar way. Now the ASR system always runs twice, and we're no longer doing any speaker tracking, and all of the breaks that used to be merged with clustering now is just merged with heat assignment like it is with any other utterance. And of course, off the bat, it doesn't really work well. So here you can see the outputs. I'm only showing the first stream for now, but on the left is the reference stream, and on the right is the output. And here is the output for the second channel. So as you can see, both of the outputs end up being the same. And so the model has collapsed. So what has happened? For one, when you do heat assignment, because there is such a strong bias for the first channel, most of the speech ends up being assigned to the first channel, and the second channel becomes pretty sparse. There is also another issue of continuity breaks. So when one speaker is talking, if there's an interruption, maybe it gets assigned to a different channel, and then maybe something else that the speaker later says is assigned to a different channel, and so on. So then the conversation is not all contained within, or like local parts of a conversation are not contained within the same channel. So what I did was first I redefined the heat heuristic to also account for the end times of the previously, like most recent spoken utterances on both channels. So here, you can see the start time orders. And what we do is when we assign a new an utterance to a channel, if both channels are available, we look at which channel has the latest end time, and we assign the utterance to that channel now. So this solves the problem of kind of like you have a decent balance of speakers in both channels, and you also have this continuity where neighboring utterances are not divided into different channels. And here's an example of how like the transcript looks like when we assign it to, we assign it with a new heuristic. And so this ends up helping the model out a lot. The first case is the original heat assignment that I showed before. In the middle, we always alternate channels. The problem with that is that, again, you break up neighboring utterances. And then in this last one, it gets pretty close to what DiCal does off the bat. And of course, there are like other smaller changes that I made to make the model more performant and to close that gap between heat condition and diarization condition, such as like reweighing the STONO mask or reordering the transcripts so that they more accurately reflect what the key outputs are. And you can see here on the real diarization labels, there's a 1.2% gap in the non-speaker attributed word error rate, and the real time factor, which is the audio duration divided by the time it takes to process that audio, ends up improving by 63%. And here is John Yu to introduce diarization.
Okay, thank you. So we work on speaker diarization, and this slide summarizes the outline of our part. So firstly, I will give an introduction about diarization, and then Mark and I will tell something about multi-channel speaker diarization. And then Prachi will tell us something about the graph clustering for speaker diarization, and then Roy and Emery will share something about using a large language model for speaker diarization. Okay, let's have a quick recap about the speaker diarization. And so in this slide, given a long input recording, the diarization system tries to get time annotations for different speakers. So it tries to answer the who spoke one. And people usually use diarization error rate for system evaluation. And as mentioned by Samuelle during JSALT, we would like to simplify, for the target speaker ASR, we would like to simplify the system. So by only use diarization and ASR for this question. To have a practical diarization system, we follow the principle of combining local neural diarization and speaker clustering. The basic idea is to split the long input recording into short segments, then apply local neural diarization on each segment and then use clustering to aggregate local direction results. This idea is also utilized by Pianode. We propose to improve the local neural direction by utilizing pre-trained models such as Wobbler, and we call it DARIZA. And so in this slide, the model is built on top of Wobbler and the conformer. This architecture generalized gave us promising results, but the pre-trained Wobbler is big and slow, which is not straightforward to integrate into ASR or extend to multi-channel processing. So we tried to apply neural network pruning techniques and managed to reduce redundant parameters up to 80% without performance loss. Like for Wobbler large, we can reduce parameters from original 360 million to 63 million. And here are results of our approved model, and we evaluate this method across different data sets, and we compare with state-of-the-art results by this date, and we found our system achieves SOTA on most data sets. So actually, what I shared so far is just for single-channel speaker direction. So during JSALT, we would like to extend this method to multi-channel speaker direction. But before that, maybe there is one important question is, why do we want to do that? Why do we want to focus on the multi-channel speaker direction? And this slide tells us some motivation about why do we want to do that. Because the microarrays are more and more common these days, and the spatial information usually helps us to discriminate speakers from different directions. But it's challenging to have a practical multi-channel system because it's usually required to be agnostic to the micro typology and the number of channels. And there is very limited research on this topic for multi-channel speaker direction. We have two ideas to do that. And so in this slide, the first one is to have, let's have a multi-channel Wobbler encoder. And the second, I will talk it later, and the second idea is to introduce additional spatial features, and Mark will tell us more about these things. And regarding to the multi-channel Wobbler, our idea is to apply a single Wobbler model on each input, on audio from each channel, and then we insert a channel communication module inside of Wobbler to aggregate spatial information. Our idea is, so the details of the channel communication module is shown in the middle of this plot. So our idea is simple and straightforward. So we just apply attention across channels instead of across frames as the original attention. And we found it works, and it's agnostic to the array typologies and the number of channels, which means no matter the number of channels you have, it always have the same outputs as the input numbers. And we insert channel communication module for the first layers, and this is how the attention looks like. So here all these attention map are obtained by averaging across frames and across attention heads. So as we can see, for different layers, the attention tries to focus on different things. Like for the first layer 0 or layer 3, the attention is trying to ignore audio from certain microphones, from certain channels, while for the layer 1, it tries to ignore the signal from the current channels. And here are the results of between the single channel, the SDMs, and our method cross-channel attention. And we found it achieved improvement across almost every data set, but especially for admitting and chime 6. And that's it. Then I will pass to Mark to tell us something about the spatial features.
Thank you very much. Okay, as Jung Yu already mentioned, I'm now presenting on a second approach how to incorporate the multi-channel information into a diarization system. And here we want to use the spatial information from the microphone array to improve the diarization. Let me start with a brief introduction of the generalized cross-correlation with phase transform, short GCC or GCC FAT. This is a cross-correlation which we can compute between two microphone recordings, and we want to use this to extract the spatial information in the microphone array, in the multi-channel recordings. On the slide here, you can also see the equation how to compute this, the GCC for a certain microphone pair, but I'd rather show you a small example to give you an intuition how this works. So let's assume we have a speaker, Bob, who's talking right now, and we have two microphones, microphone A and B, recording him. Now, because of the positions in space and because of the limited speed the sound can travel with, the sound will reach microphone A slightly earlier than microphone B. Therefore, the speech signal will be slightly delayed in the recording of microphone B compared to the recording of microphone A. This is the image on the left here, where we, for the example, assume a delay of 5.5 samples. If we now compute the GCC FAT between these two signals, we will get a correlation which exhibits a peak like this, exactly at the position lambda, equal to the delay between our two signals. So by finding this peak in the correlation and identifying the delay, we can find the certain delays each position exhibits in the correlation. And by combining the delays of multiple microphone pairs, we can distinguish the different positions and therefore the speakers speaking from the position between each other. This is all in the case of single speaker, where only one speech signal is reaching the microphones, but in the case of overlapping speech, multiple speech signals are reaching the microphones simultaneously. This means that each speech signal reaching the microphones from a certain direction will create one peak in the correlation. These here in red marked are two peaks created by two real physical speakers, and also reflections of the speech, for example, on a window or a smooth surface, which reach the microphones from a different direction, can create additional peaks at a delay where no physical existing speaker is active. This can make the peak detection and the finding of the delays of the real positions a bit more difficult. Now, while the pictures I've shown here are always the correlation computed for one certain time frame, we can compute these correlations for all time frames and stack them together to get a picture like this. Here we see on the y-axis the delay lambda, on the x-axis the frames t, and the color map corresponds to the height of the correlation. So in this image we can see that in the beginning there's a high correlation for a delay around -2. Then at the following frames shortly a different position is active at a delay of around 3, and then for a prolonged time another speaker is active. I wanted to show this to give a motivation how this is useful for diarization, as this already looks quite similar to the estimated diarization of output of a system. Now the big question is, how do we use this now? So our goal here is to use the diarization system which Zheng Yu just presented, and we want to incorporate the spatial information in a way that is also microphone array geometry agnostic, but also agnostic to the number of channels we have. So as a very short recap, we have the single channel system from diarization, which takes waffle M features from the single channel input, feeds them into a conformer, and gets a local diarization estimate. Now we extend this with the GCC features, the spatial information. The first part stays the same. We still extract the waffle M features from the single channel from the first channel input and take all the other channels to compute the GCC for all channel combinations. This results in multiple GCC outputs basically at this point. And to be agnostic to the number of channels, these are aggregated in a GCC encoder network. And the aggregated GCC features are then combined with the waffle M features, fed into the conformer to again get the diarization estimate. Here's a look into the encoder architecture. This is illustrated just for 2 channel pairs, but in the experiments this takes 1 branch like this for each channel pair. So it consists of multiple layers of self-attention, and between each layer of self-attention, the different channel pair branches are connected in a tag-like fashion. That means the feature is transformed with a linear layer. They are averaged over all channel pairs and then concatenated to each branch. That's the red piece concatenated to the blue one, and then fed through another linear layer and fed back into the original branch. This allows an information flow between all the different channel pairs so that the information from each channel can be exchanged with the information of each other channel. Here you can now see the results. We evaluated on the datasets AMI, LA meeting, not so far, AI shell 4, and Chime 6, which is also the datasets trained on. And in the first layer, you can see the baseline system, the DiaryZen system with a single channel. And below that, you see the extension where the GCC features are used with an input of 4 channels. And over the datasets, we see an improvement by including the JSALT features by up to 0.5% in diarization error rate. The next steps are to evaluate further on all the multi-channel input and also to further optimize the fusion of the two different features inside the network. I will give over to Prachi Singh now. Oh, sorry, yeah?
Yeah, just a question. So basically you also always have a combination of only 2 channels, or you fabricate something more complex, for example, for an 8-channel array? Or so is it like then 8 times 7 combinations of always 2 channels, which means quite a big number?
So for the GCC is always computed between 2 channels. That means from all the input channels taken, you can take all different combinations of 2 channels of these always. And then for each 2-channel pair, you compute, or there's 1 GCC computed per frame.
Okay, so it's quite a number actually. If you have, for example,
yeah, with a lot of
or 16
channels, the
array.
number increases.
Okay,
yes.
thanks. Not to break my bone.
All right. If you go back to that picture where you showed the GCC output, it was one of those MATLAB plots. Yeah, that one.
This one?
Yeah. I was wondering, looking at this picture, and then let's keep this picture in mind and go to your next slide or 2 slides forward. Yeah, this one. So before you combine it with the VAV-LM features and all that, I was wondering whether there is a way to train this GCC encoder or pre-train it or something with the actual diarization picture. So basically, figure out, because that was a very nice picture and one peak was very clear. In reality, there might be multiple peaks. So I was wondering if there's a way to train this encoder intrinsically first, just to be a good representation of the diarizer. Any thoughts on that? I mean,
so what you're saying is to pre-train the encoder to directly give a diarization.
The diarization output, and then worry about what to do with the VAV-LM features.
I have not tried that, but maybe that's possible to extend the encoder for that. What I have tried is to take away the WaffleM features and simply take this network architecture with basically the conformer after the encoder to train only on the GCC features, the diarization. You could say that the old encoder together with the conformer is the new encoder, and then it was just an encoder. But
yeah, what I'm thinking is the encoder with something, I don't know, maybe like a conformer is the diarizer. And just train it as a diarizer. Don't worry about cleaning anything up. And it's just a feeling that maybe we should have something intermediate to sort of get the encoder to give out better features. Just a thought. I don't know. We can talk about it later.
So in the experiments where I used where I used the system without the WaffleM features, basically the system with only the GCC features as information.
Yeah.
This when I trained this, it reached not comparable with the WaffleM with the DiaryZen system performance, but it reached performance on the development set below 30% diarization error rate. Okay. And then I also tried to use from this system pre-trained GCC encoder in combination with the WaffleM features.
Okay, so you did do something. Okay, so let's maybe talk.
So it goes into this direction, but it's not. It's basically a different encoder structure if you want to go directly to diarization without the conformer. I didn't test that. Okay. Maybe that holds some more information.
I know. Yeah. Okay. All right. Thanks.
Hello everyone. I will be talking about supervised graph clustering as an extension to Dirizen. So as Jangyu has already told about the Dirizen model, it has two main components. One is the local segmentation module, which give out this speaker activities for each chunk of say 8 seconds. And then we have multiple chunks, but there is permutation invariance, because of which the same speaker can land up in another speaker's activity. So the next step is to extract speaker embeddings out of the clean speaker regions, which doesn't have overlaps, and then pass it to a clustering module, which can give us global speakers, which we can plug it to this speaker activity. Now I have identified two problems in this. First is that speaker embeddings extractor was trained with clean speaker embeddings, clean speaker segments. But here this model can output noisy segments which can have some influence from the other speaker, as well as there are some edge cases like most of the portion can land up in the overlapping regions and can be ignored by the extractor, or maybe some speaker is completely overlapping all the time with some dominant speaker. So then next issue is that the clustering is still unsupervised, so there is no going back to optimize it jointly. So that's why I propose the first solution is diarization condition speaker embeddings, where we can train with multi-speaker audio segments and then use frame level diarization transformation, which is similar to Dykov as mentioned by Alex, for masking like this STNO mask for the target speaker. And then this will, then we can compare this output with the target speaker, clean speaker embedding, and try to reduce the gap between them. This helps to handle the overlaps and silences within this embedding extractor. Now this can be extended towards the supervised clustering, which is based on my previous work, which is supervised hierarchical graph clustering. And here we perform the supervised clustering using the graph neural network, because they have very beautiful architecture which can take the graph as an input, and if we treat the speaker embeddings as the node of the graph, and we can generate a k-nearest neighbor graph where the edges are the similarities based on cosine or any other metric. And then we can train using some similarity loss, and then we can backpropagate all towards this embedding extractor. And then this can help us to make the module more conversational dependent, and this is an ongoing work, so I don't have results, but this paper has some good results which made me think that this is a better option. So with this, let me conclude. So clustering still remains an essential part of the diarization, and optimizing the speaker embeddings and clustering can help to make better models with better domain adaptation. And this is also scalable to the multi-channel diarization, which my teammates have already discussed. Thank you. Okay, so let's move on to the next topic by Royal.
Okay, let me introduce our work about streaming speak dilatation using ASR with the turning point and the large language model. The motivation is the large language shows strong contextual modeling ability. You can say it's example if you just input some text to speak text and give it prompt that GPT to do some text-only dilation, the GPT can do it well, but there are still some errors. dilation now from text alone only, I think is very difficult. We do some text on the open source dataset AirShell 4 and find that the CPWR is very worse. So we want to explore whether large language model with speaker embedding for dilation, maybe it will be better. Traditional family dilation, they first do the segmentation or local dilation to get some short segment. Then they extract their speaker vector and to do some clustering to assign each short segment with a speaker label. But the semantic level doesn't do like this. They do the ASR first. They do the ASR with turning point, and you get some sentence level long segment. Then you can extract from this long segment, extract some speaker embedding or text embedding. Then you can do assignment, do some clustering, and assignment this long segment with some speaker label. Let's go to some details. Okay. Yeah, with speaker change, the shop is the speaker change token. Yeah. Okay. Let's go to some detail about the streaming speaker dilation using SR with turning point. First, we use some SR model with the turning point prediction to predict the SR result like this. The shop token is the speaker change. Then we can use this turning point boundary to extract some speaker embedding. Then we will compare this speaker embedding with the history class center. If this speaker embedding is close to some history class center, then we can assign the history class speaker to this segment level extractor. Or it's not close to the history class center. We think it's a new speaker, and the history class center will be like this example from 2 to 3. Yeah. We call this is extractor only system. It's audio only system. It's only use the acoustic information. And now we bring in the large language model. The first stage is the same like before, and we still extract some associative information, X vector. But now we also use the large language model to extract some textual information from the ASR output. Then we can get some token level text embedding. Then we just contact the associative embedding X vector with the text embedding. Then we can get some associative semantic vector. Then we can use this vector to just use the X vector to do some streaming speaker dilation. We call this the light fusion of the multimodal embeddings, because the fusion occurs after the large language model. We do some tests both on the in-domain, in-house meeting test data, but also some open source data like AirShell 4. We can see that text-only system just use like some GPT performance very poor. But the X-Vector audio-only system can get some reasonable performance. But when we get them together, we both use text and audio information, we achieve the best results. Yeah. But also, if you read some streaming speaker dilation paper, you will find they use a metric called word dilation error rate. But when we use this metric, we find some question. You can see this example, the word dilation error rate computed like this. It only considers that correct ASR result and the incorrect ASR result. They don't consider the insertion error and the deletion error. So there is a very confusing problem. If the sentence is only insertion error and deletion error, no, the WDR is 0. It's very strange. So we now process a new metric. Now we just call this WDR new. In this metric, we both consider the insertion error and the deletion error, and we find this metric have more linear relationship with the WDR. Maybe this metric can be a better metric for the ASR and the derivation system. We will do more after the workshop, I think. Yeah, that's all. Emma will introduce more about the text-only speaker derivation. Yeah.
Okay. Hello. So until Brno started talking about his work, what you saw was about doing diarization first and then conditioning ASR on that. But we can also flip that approach to do ASR first and use the semantic information to help diarization like Brno presented. What I worked on is, can we use only text to do speaker attribution? So can LLMs diarize? Can we do this without any audio through only text? Yeah, so there has been work on using LLMs for diarization before, but they are mainly in the context of error correction, not doing full-on diarization or speaker attribution. So why is this feasible? Is that mainly diarization and speaker attribution, we want it on top of transcriptions. We don't want diarization or speaker attribution when someone speaks alone. We usually have transcriptions, and we want to do speaker attribution on top of that. So why would we ever want from only text speaker attribution? If you have a single speaker foundation model like Whisper, then you can use that type of ASR output, use the textual speaker attributor model on top of it to get a multi-talker, multi-speaker ASR model. But also it can be used on top of existing model, which does pretty good in multi-talker ASR without speaker attribution. If you remember what Shiloh presented about heat-conditioned Whisper, because it has only 2 streams, it doesn't have speaker attribution, but it still does pretty well on multi-talker ASR. So we can use a text-only speaker attribution model on top of these type of things. So more concretely, what we have are some utterances, and we want to get these utterances in text to their speaker labels. These utterances come from ASR models, where the ASR decides the segmentation. Because it outputs in utterance level, not on word level, the segmentation already comes from the ASR module. And this is an actual example from the call home data set, where you can see the utterances, and you can also see diarization output from Pianote. Pianote is the state-of-the-art diarization module right now, but still you can see that it makes some mistakes. For example, on the first utterance, it says, and Anders is a different speaker. This is because of different acoustic conditions and noise shifting its output. However, when we look at it semantically, it is very clear that that sentence should only be attributed to one single speaker. So this is another motivation that we can use text to do diarization. So how did I attack this problem? The goal is to predict the next speaker given the previous utterances that are labeled. So I have some context utterances, and I know their speaker labels, and I try to get the probability of the speaker for the new utterance. To do that, I'm using LLMs, or language models in general, but this will mostly focus on LLMs, and getting the probability for each speaker. But to be able to do this on context and not to get trapped on previous errors and not to propagate errors, I'm doing beam search on these probabilities. And also, even though this is more long context than just audio, you can still go over context on the transformer models. So there is a sliding window for the previous utterances that I give it. The main thing here is the scoring function, which gives you the probability of the next speaker. So there are two ways you can use the LLM. You can use it as a language model, as what it is, or you can use an instruction-tuned LLM as a general helper, as an LLM as a judge, and I will show how I use that. So the baseline is the language model case, where you can use LLMs, you can use n-gram models. This is no context, meaning it only sees the previous utterance, not the utterances before, and you want to predict the speaker label at time t, so you get the last utterance from each speaker you have, and you also get your new utterance, and you get the conditional probability of the new utterance given the previous utterance of each speaker. And whichever is the maximum probability speaker, you choose that as your speaker. Or you can use the instruction-tuned model as a more contextual representation. The motivation here is that LLMs have shown great capabilities on diverse tasks, so can it also do this, where we give the LLM the labeled speakers, the previous utterances as a conversation, and just ask it, this is the new utterance, which speaker said this utterance? And I fine-tune this on the train sets of conversational data to get this type of output. Yeah, also, you might also notice that there is actually a smaller problem inside this large K-speaker classification problem. Instead of classifying which speaker it is, you can also just classify whether there is speaker change between utterances or not. So you have an easier binary classification problem. And I trained an encoder-only model that takes two utterances and decides whether there's speaker change between them. This helps the model to be more robust, and it also helps it because if in the sliding window there is only one speaker talking, the model forgets all previous speakers and just starts outputting that, but the speaker change model helps prevent that catastrophic forgetting case. So I tested this on Callhome, which is a two-speaker telephone data set, and also on AMI, which is a four-speaker, on the test data, a four-speaker meeting data set. And you see the CPU error rate that Alex already introduced. And the confusion is diarization error rate, but only the confusion part. So diarization error rate computes confusion, insertion, and deletions. However, the insertion and deletions are being done by the transcription, the ASR module here, so this module is only responsible for the confusions, and you can see the results with a trigram baseline and a LLM baseline on the table. The Callhome results are actually promising, where you can get 23% CPU error rate just using this module on a single speaker whisper. But it still performs poorly on AMI data. That is because it is not, the LLMs are not very good at detecting whether the different speakers are really different. While it can do some amount of, oh yeah, this is a different speaker, it is not good at detecting which speaker in the previous context it was. So the main work that I will be doing after this is to improve how to get better signals from the LLM for this. But this model still shows that it is promising, especially on the Callhome set, and then this type of speaker attribution models, maybe by themselves, or maybe like Roy presented, combined with audio information, can be helpful going forward on multi-talker ASR.
I'm slightly puzzled by the fact that you have, let's say under CPU error rate, you have two numbers.
Oh, yeah.
The second one tends to be smaller, but you're saying that the second one is the result of working on the ASR output, whereas the first one is working on ground truth.
Yes, exactly.
Can you say what's going on?
Yeah, of course. Just to say what's going on here, the first ones before the forward slash are on ground truth, not transcriptions, the ground truth words, and the second one is on actual ASR outputs. The actual ASR outputs actually perform better. The reason is that the segmentation done by the ASR actually helps the LLM more than when you just use rule-based segmentation from the ground truth. So the LLM can understand the utterances where the ASR decides better and do much better on the attribution. Yeah.
Could you easily do a contrastive experiment where you align the ASR output with the ground truth, then segment the ground truth transcript according to the ASR segmentation, but then do the speaker attribution on that new? What I'm trying to figure out is, you're proposing, and you may be right, that the difference is that these chunks are somehow more amenable for diarization. So in that case, let's find out how much is lost by the errors rather than confounding the two.
I see. Makes sense. I didn't do that experiment, but it's worthwhile. Yeah.
It should be easy to do, right?
Yeah.
Yeah, okay. Yeah.
Okay, if no one else has more questions, it is break time, and you can go wake up. So, yeah. Thank you.
So, oh, sorry. Before you start, we have a question from Paula. She's asking, do you have any intuition why Chime is not getting any improvement? I think it's more to Alex, or...
No, Dominic, you can answer.
What was the question?
Why Chime is not getting any improvement?
But it was diarization related, right? So, Jangyu?
The thing is, I guess it's for Mark, because... no, I mean, because the channel can connect, cross-channel attention method get improvement on Chime and a significant improvement on Chime. But maybe I get it for Mark. Yeah.
So I'm assuming it was for me, yes, because on Chime I didn't get some significant improvement compared to Jangyu, and so far I'm speculating that the non-improvement on Chime is maybe due to the more complicated audio scenario, and that the detection for the peaks in the generalized cross-correlation can become more difficult, and that the system doesn't really detect the speakers being active there. So, does that answer the question? Oh, yeah. Okay.
Maybe I can further speculate, because as Samuelle has said, there should be on Chime 6 should be quite some maybe the audios are not in sync. So the audios from different microphones are not in sync. So maybe they are so much out of sync that basically the GCC features are not even able to see the...
He's using one device, but the devices can be scattered across rooms. So we suggested like some changes about that. Like you can use 2 microphones for each device and then stack them. Like you can compute GCC FAT on each device and then you stack. But yeah, we'll do it, I don't know, next week.
All right, should we move on? Okay, so so far, the guys before me just described the parts of our pipeline, which was target speaker ASR and diarization. But we're still missing one letter from our team name, which is E, and it stands for end-to-end. So this is what our sub-team was focusing on. And right now, I'm going to cover like a truly long-form end-to-end ASR and end-to-end target speaker ASR and diarization. So let's imagine we have a conversation of 2 speakers. There can be some overlap here and there. And basically, real diarization produces some errors. It's not going to be perfect. But these errors usually in our pipeline propagate through the ASR system, which can hinder the performance and basically affect the quality of transcripts. And also, the DICOM model was trained using Oracle diarization labels only, So basically, it's mostly unaware of some mismatch between the SDNO masks and the acoustics. So we cannot basically, on its own, fix some errors. So that's where the end-to-end or joint training of diarization and target speaker ASR comes to a game. So what we actually want is the speaker diarization does not really have to be 100% accurate. We don't care about frame level precision as long as some, for example, segments encapsulate the entire words. But also we want ASR to like learn to fix some mistakes that basically are produced by diarization. So basically we want to make sure the entire system from diarization to target speaker ASR is really robust towards some errors. So let me touch on the target speaker ASR first. DICAO, as you heard, is based on Whisper, and many of you know that Whisper handles 30-second chunks only. It's basically, it was trained that way, and even during inference, if you have, for example, 1 hour long recording, you need to still chunk it into some shorter segments, process segment by segment, and that get the entire transcript for the entire recording, which basically complicates the joint training, right? If you want to train on longer segments, we would need to do some chunking of ASR, and then do some diarization, and then do some nasty tricks in order to make everything work. So we were searching for replacement, and when we were looking at the open ASR leaderboard, we saw Parakeet from NVIDIA, which is quite, I mean, at that time it was performing, I think it was the best model on the open ASR leaderboard. So we said, let's just change Whisper, and let's just let's replace Whisper with Parakeet. And the advantage of Parakeet is that it's naturally long form. So how it works is that you have some utterance here. It can be even 1 hour long utterance. Then you basically pass it to conformer, which is transformer that contains some convolutional layers in it. And then we obtain some acoustic features, and then use our RNT decoder at the end, instead of the attention decoder that is used by Whisper. And there are a couple of advantages here. So first thing is that RNNTs are basically naturally streamable, which means that we can turn the entire model into a streaming target speaker ASR model. And also, we don't really need to train Whisper to produce some we don't really need to train the model explicitly to produce any timestamps, because we just can compute the timestamps from the decoding itself. So here, if we replace Whisper with Parakeet, we simplify the entire inference, and basically we can just do a single forward pass through the model and obtain the final transcript. So let's look at the results. If we compare it to DICAO, we can see that the diarization condition Parakeet mostly outperforms the DICAO model. And here we also can see that, for example, on AMI, which recordings can get up to 2 hours long. Basically, we don't have any number for the full attention model because we cannot really fit into memory. But what we can do, we can replace the full attention with local attention. I'm going to be describing the local attention just in a minute. But we can see that if we do it, we can just pass even couple hours long recordings to the model and obtain transcript just in single forward pass. So we're really getting rid of the chunking inference there. And we can see that even if we replace the full attention with local attention, we're not really losing performance here. But okay, we have target speaker ASR that is naturally long form end-to-end, so we can just go to diarization because that's the second ingredient we need for the end-to-end training. So Jiangyu presented you the hybrid system, the diarization system, but let me just recap how it works. So you have some audio, you need to chunk it into shorter chunks, let's say 16 seconds. Then you apply some neural diarization model to obtain some per chunk diarization, but then you need to stitch these segments to obtain the full recording diarization labels. And for that, we're using clustering. But basically, you cannot backpropagate through clustering. So if you want to do the joint training, and if you want to train ASR and diarization in an end-to-end fashion, we cannot really use this system. So we need a replacement, and that's basically where that's why we need to use the end-to-end neural diarization systems. So just to describe how these systems work, it's quite simple. You have utterance here, then you have some transformer-based model or some neural network, and then in just one forward pass, you obtain the entire speaker diarization outputs here. However, we know how meetings can be long sometimes, right? A couple hours here and there, and basically we cannot infer the entire diarization for a 2 hour long recording with full attention models here. So again, that's why we have some attention variations, and instead of the full attention model, that basically for each query you can attend to all the keys, we need to replace this attention with something called sliding window attention, or basically there are some other variants or variations, but basically here we have the sliding window attention. So, but if you replace the full attention with sliding window attention, we really cannot basically summarize the entire information throughout the entire recording. So that's why we need to use something called global tokens. So we basically have something in between. We have some tokens that can attend to entire recording, but at the same time we have, like most of the tokens can only attend to some local surrounding of the current embedding. So this seems like a promising way of building like truly long-form end-to-end diarization models. And that's what I've been focusing on this workshop. So basically, my architecture here is that I have some acoustic features. I add some global tokens at the beginning of the sequence, and I apply conformer encoder. And here I'm using the global attention, like the local Windows lighting attention with global tokens. And then I obtain some acoustic embeddings here. From there on, I compute something called attractors. These embeddings basically serve as embeddings that attract some embeddings of speech. And from there, we can compute the speaker probabilities here. So basically, we, in 1/4 pass, obtain the entire diarization result for the long-form recording. So if you look at the results, I was mainly training on longer segments, up to 10 minutes. And it's really challenging, because if you're training on long segments, the sequences themselves are long, but also the labels are quite sparse, which makes the entire training more challenging. But also, basically, if you're training long form, there are some other issues with the training that I'm not going to comment on. But also, if I look at a training setup, I was pre-training on Yoda's data, which were labeled by Pinode. So basically, thank you, Pinode, for providing us data for training. And then I was fine-tuning on AMI. But even though I was training everything on log-form recordings and a lot of data, I still wasn't able to get really good performance. So I got 38.6% DER, and I'm still working on this model. But what's more important here is inference time and also memory consumption. So if you look at a comparison between the full attention model and the local attention model, we can see that if you're inferring half-an-hour recording, already the inference is a lot longer than basically when using full attention model compared to the local one. But what's more important is the memory consumption here. With half-an-hour recording, we're already at 32 gigabytes, and if you want to infer 1 hour recording, basically we just run out of memory issues. But it's not happening with the local attention model, where we can even infer 2 hours long recording, and it's just going to consume 20 gigabytes. So we still have plenty of memory left. So just to sum everything up, we really need some ideally long-form end-to-end target speaker ASR and diarization for joint training to make the systems really, really more robust. And it seems like NVIDIA parakeet models or other long-form models basically outperform or are comparable to DICO and are actually basically handle long-form, which enables us to really easily do end-to-end joint training. And then that local attention-based diarization is fast and handles long recordings. But right now, it slightly, not slightly, but a lot underperforms the models like Diarizend. So there's still a lot of work to do on long-form speaker diarization model training. And also, some other part that I'm going to be focusing on after the workshop is going to be the joint training. So yeah, this is all from me. And now Darshan is going to present his adaptive chunking.
Thank you, Dominic. So like Dominic, my main area of focus during the workshop was on long-form speech processing, particularly long-form ASR. So in the next few slides, I'll quickly summarize our work, adaptive chunking, which I was working throughout the workshop. So to quickly summarize, the most common way that people perform long-form speech processing is if you have a long audio that's coming in as input, you chop them into fixed size chunks, where W is the size of the chunk. Then you process each of these chunks individually. Here, processing is basically a neural network, which could be transformer, but the attention constrained within the chunk. Now, because you want to also have information being communicated across the chunk, you have some sort of global information pooling, like the concept of global tokens that Dominic just mentioned during his presentation. Now, what is the problem with such a setup is, because W is a hyperparameter, it could be pretty sensitive to the choice of W, and if you are not careful enough, you might do some premature chopping of the audio, which would make the task much harder for the model, because it also has to now learn how to process the information across the multiple chunks. So we wanted to get around this problem. So our proposal was, why not let the model learn how to do the chunking during training end-to-end, and hopefully it learns to chop the audio into dynamically sized chunks, which are hopefully self-contained. So how do we do this? So first I want to walk you through what we want to do during inference and then track back to how do we achieve it during training. So if we have a long form audio coming in as input, you get the corresponding feature sequence, which is shown in the figure. Now we pass this through something called an MLP layer with a sigmoid activation. We call it chunker. And this, for every frame, gives us a probability that a chunk boundary could exist at that frame. So naturally, the first and the last frame will always have the probability of 1. Now, once you have these probabilities, you can either do sampling through a Bernoulli distribution, or you could threshold the probabilities to determine exactly what are the chunk boundaries. Once you have the chunk boundaries, you proceed as usual, like how you process the fixed chunking setup. Now, what is the problem with training in such a system? The moment you introduce sampling or thresholding, it breaks the computation graph and you can't train it end to end. So to overcome this problem, during training, we use something called attention biasing. So here you have your scores, which are nothing but query key outer product computations. To this, you add an additional bias term, and all it is telling the model, telling the attention is, look, so these are the positions which are important to me. Try to skew your attention towards those positions. So mathematically, this is how it looks like. So you have your QKT computations. To this, you add a bias term, which is log alpha. So now it all boils down to how do we construct this matrix alpha. So this is how we define it. So alpha ij, you can think of it as the probability or a score that frame I and frame j belong to the same chunk. So if you think about it, you ideally want the attention to be biased more towards frames which you know for sure will end up in the same chunk. So then how do we calculate these alpha ij's? So this might look like a daunting equation at first, but it essentially has two components. So first, you want to marginalize along all chunks that contain both I and j frame. You have to do this because it's dynamic chunking, so you have to loop over all possible chunks. Now, once you have the chunk, you basically want to identify what is the probability that that chunk will ever be formed. So you have two high probabilities at the beginning and end of the chunk, and then low probabilities all the way in the middle. So, well, now you have the equation. So you can efficiently compute this using the DP formulation. I won't go too much into details. But the interesting part is this formulation also allows us to compute the gradients very fast. And now you have a fully functioning layer with both the forward and the backward computations done using CUDA computations. We did this. We inserted it into an architecture, and we tried on LibriSpeech. And when we compare it against the chunk transformer and a full attention transformer, looks like it does slightly better. So then we wanted to look at the attention plots to see whether it's actually doing what we expect it to do. And in most of the attention layers, we see that it nicely splits the audio into some dynamically sized chunks. But then there are also some degenerate cases where it tries to get around this problem of chunking by either doing full attention or not doing attention at all. So we have still a long way to go. I've given a very high level bird's eye view of what we did. There are a lot of other training strategies and things we had to introduce, but I won't go into those details, and hopefully we take it forward after the workshop. Next, Rohan is going to talk about how we address the problem of data scarcity. Thank you.
So I guess the motivation to do this was, again, like Dominic said, to mainly reduce memory usage and increase inference time. I know that you're not fully happy with the way the automatic chunking is happening, but given what it's doing, how much speed up do you see? How much reduced memory usage do you see? Do you have any?
So currently we don't see any speed up, mainly because we are still doing quadratic computations. But to mitigate that, we were working on something called windowed chunking, where we say we also limit on how big a chunk can be, and then you constrain and then you end up saving quite a lot. But we saw that there are a lot of problems in training the system, so we didn't add it in the
I see. So what you're saying is the way you're doing it right now, even though it is chunking, and so your computation should be like, number of chunks times the quadratic in the length of the chunk. Yes. And the number of chunks will be something like, I think square root of t might be the optimal, right? Because then you'll get order t within the chunk and you'll get times whatever. I don't know. So you're saying that that's not happening, the chunks are still too big?
So the problem with that setup is, so you expect the probabilities to also follow the maximum chunk window setup, which you don't. So you have to have additional losses to kind of force it to do it. So it becomes quite complicated, so we didn't want to. So we are still working on it, but we don't have any promising results so far.
I see. I guess it's, so the memory will go the same way. If you're not doing good chunking, then you won't save memory either.
Yes.
Okay, all right, okay.
Thank you.
Thank you. So now, based on what Darshan and Dominic presented, for long-form ASR and diarization training, one of the very important things that you need is data. So for the types of long-form diarization models that Dominic is trying to train, he's trying to train about an hour at a time in each forward pass. So for this, you need a lot of real multi-talker conversational data, and there's not enough of this conversational data of real conversational data in existing corpuses. Part of this problem stems from the fact that it's really hard to annotate some of this multi-talker noisy speech. We want this to be sort of in the wild, speech is noisy, there's multiple speakers, normally the microphones are far field, and there's sort of varying acoustic scenes, reverberant mixtures. And to sort of train the models that Dominic and Darshan are trying to train, you have to simulate data in some form to have enough data to train their models. So some of the current simulation methods are not necessarily very realistic. They don't sort of accurately represent the distributions of real speech. Some current ways of simulating data might include LibreMix, which is overlapped sort of samples of single speaker talk, but this doesn't necessarily exactly capture turn-taking dynamics. There are a couple of sort of openly used multi-talker, like text-to-speech or speech synthesis models, but a lot of these are trained on very clean, studio-like speech, which don't necessarily expand to various acoustic domains and don't really expand past two speakers. So the goal of what I was working on was to extend existing pre-trained single-speaker text-to-speech models and to generate multi-talker, conversational, noisy sort of meeting-type audio mixtures using fine-tuning. This is in some ways similar to what Player Part also presented in sort of generating a audio mixture from a dialogue. The goal here was to do it in an end-to-end fashion, somewhat like this, where we have a single speaker TTS, so we'd start from a pre-trained model, and in the simple case of a two-speaker generation, we'd have an individual generation from each TTS model, and then have a connector model in the middle. This would be something similar to a sort of cross-speaker interaction module that some of my teammates presented earlier. One example of this could be the transform average concatenate, or the TAC. This was originally presented in work for speech separation, where it's able to sort of provide sort of pooling of information across speaker 1 and speaker 2 to condition each speaker on the other one. So in this case, what we'd want the end-to-end system to output would be to learn that from this initial utterance, hi, how are you, you would learn that, oh, okay, after this first segment, there's probably going to be silence because the other speaker is going to start speaking. So we learn these inherent turn-taking dynamics through this speaker interaction module. So now we can listen to a quick demonstration of So this is an example. So that was the real conversation, and taking that transcript, we try to now generate that same sort of audio with the trained model. So there's some sort of promising results there with, we kind of hear two speakers clearly, we hear some background noise, but at the same time there's some issues as well, especially when there's overlapping speech. One speaker is, the intelligibility of the speaker is greatly reduced, and there's some issues like this. So far during the workshop, kind of if you evaluate that on sort of turn-taking metrics, if you evaluate like the average duration of each speaker's turn, the amount of overlap, you see sort of an improvement compared to like a modular strategy of generating speaker A, then speaker B, and concatenating it. But at the same time, training in the sort of model that I was trying to train, there's some challenges with intelligibility. And so especially in that audio, we could pretty audibly hear there was a lot of artifacts during the generation, as well as when one speaker was speaking, you could hear one speaker clearly and the other one starts to sort of mumble and the intelligibility goes significantly down. Pretty poor word error rate there, where word error rate is sometimes used to measure the intelligibility, and we see 85%, especially on that second speaker in that overlapped speech. So those are some areas to improve on, and then hopefully the goal of this would be to provide or produce an end-to-end model that can simulate data for multi-talker ASR in the context of what the team is doing. And now I'll hand it over to Matthew to speak about.
Thank you. All right, so up to this point, you guys have now heard all of the letters of our team's name. So we're gonna take a small step back. So we've built a lot of things around DiCal and around DiaryZen, and now you've seen how to extend it out to end-to-end training. But we also care about alternative supervision schemes. This is alternative ways, basically, of formulating the problem, and we've looked at it through the supervisions. And I put multi-talker in parentheses because some of what you'll hear is slightly more general, actually. So again, here's our talk about multi-talker ASR. There's a diarization and an ASR component. And so here's a little simulated transcript. So there's a few parts to this that you'll hear alternatives for. One is the whole thing, speaker attributed ASR. So you'll hear my colleague Martine talk about that. Now we can also treat the problem separately and focus just, for instance, on transcription and alignment of multi-talker ASR. And then you'll also hear about diarization-specific tricks that we can use to reformulate the problem.
Okay. So I will start just by my part by repeating what Alex already mentioned in the presentation. So as you already know, the DICO struggles to correctly recognize the fully overlapping regions. And the issue is that the STNO masks are almost identical for these overlapping speakers, where we actually want from the model. So the problem is that those masks are almost identical, and we want for the model to produce two different transcripts. Okay, and this STNO ambiguity can lead to speaker misattributions and duplicate transcriptions. The other issue is that the target speaker ASR, as DICO is, models each speaker independently, like it is shown here on this figure. So the decoder doesn't consider the other speakers in the mixture. And to overcome all these issues, we are proposing to model, to have a single decoder to produce interleaved speaker attributed transcripts like I have here. We are actually proposing to have a single decoder which can actually take a look into other speaker speech and produce this SOT style transcript. We do this with the serial output training. And the serial output training framework has already been proven effective in previous works. And in this work, what we are actually doing is that we are taking so our work is still based on the DICO. And what we are doing is that we are taking the DICO encoder embeddings and concatenating them together to produce one long sequence of embeddings, which is then used to condition the whisper decoder. The whole model is trained on transcripts, which are serialized based on the timestamps. Okay, on this slide, I have a real example from the AMI dataset. You can see here the cross-attention weights from the AMI recording. And on the y-axis, we have correctly recognized transcripts, which
which actually compose queries to the cross-attention for the next token prediction. And on the x-axis, we have actually 3 different speaker. So we have 3 different we have 3 different whisper encoder embeddings which are concatenated into one big key sequence of embeddings. And these 3 whisper encoder embeddings correspond to 3 different speakers: speaker 1, speaker 2, and speaker 3. And in the main area, we have the attention weights. And what I'm trying to show in this example is how our proposed model works. So, as you can see, the decoder first takes a look into the first 8 seconds from the speaker 1 and transcribes those 8 seconds, as you can see on the y-axis. Then it jumps to the second speaker. Then it jumps also to the first speaker. And what is more important, the model is able to jump back in time to the first speaker to transcribe the rest of the speech from the first speaker. So this is how our model works. And there is actually one other interesting question, and that is, can we extract actually alignments from these cross-attention weights? And the simple answer is yes, we can, but somehow we need to convert those soft probabilities or those probabilities into hard decisions. And I think that this can be actually tricky, and you might get some unreliable alignments. And actually, this topic of extracting the alignments is a topic of Matthew Wisner, and he will show us how we can do it more effectively and more reliably. Okay, and this brings me to the results of our proposed DICO. So we evaluated our proposed system on various multi-talker datasets. We evaluated on the AMI SDM, which is a meeting-like data, together with the not so far, which is also meeting-like dataset. But we also evaluated it on the artificial mixtures on Libri2Mix and Libri3Mix, both clean versions and clean and others version. And in addition, we also evaluated different SOT transcription styles. So first style we call speaker style transcription, and it actually, in this style, the transcription is composed speaker by speaker. And in the other style, we have this alternate style where when the transcription is composed segment by segment based on the starting time of the segment. And as you can see from the results, our model performs quite well on the artificial mixtures, while it performs worse than the original DICO on the meeting-like data. And the issue on the meeting-like data is that we have problems with the correctly assigning speakers to the segments. And since we are using the CP order rate, which is actually a speaker-dependent metric, and if we actually incorrectly recognize the speakers, the whole segment is considered either as a deletion or insertion. So that's why we have worse results than the baseline. Okay, so that's it from my side, and I will pass word to Matthew.
You have a question?
Yeah.
So I'm thinking about what you're doing here, and I'm thinking that, what you're trying to do is essentially take the original DICA formulation where it would have decoded the same audio 3 times, and you're still making it decode the same audio 3 times because you're concatenating 3 copies of the encoder embeddings. The only thing you're doing is you're now presenting it the transcripts in some order and expecting it to jump from one to the other. And so in some sense, I don't have a clear intuition for why this should even do anything different other than the decoder has a chance to pay attention to the other speakers.
Yes,
right? That's the only thing, because the
the
encoder is not exactly the same.
Yeah, that's the main thing. The decoder is aware of other speech.
Right.
And he can learn that if he transcribes some part, he doesn't have to repeat the same part twice.
Maybe. I mean, there is overlap, so it's not like it can ignore it. And also, let's say that the diarization was incorrect or something, right? It's not, I don't see the decoder, for example, for speaker 2 assuming that there was a diarization boundary error in the 2 to 5 seconds, maybe the second speaker began already at 1. It is not paying attention to the other chunk where 1 is present and so on, right? That's one issue. The other issue is that this is just from my understanding, if I took only one copy of the audio, then this would be standard SOT, because now you just have one audio and you have 3 different transcripts, and even though there is overlap between speaker 1 and speaker 2, you're going to concatenate the transcripts. So it has to first produce the speaker 1 transcript and then speaker 2. So you're still doing SOT in that sense, except you're giving it 3 copies or as many different copies, right?
Yes, this is actually the main disadvantage of this approach.
Right. So what would be standard SOT on this task?
You will have just one encoder and one encoder embeddings and...
No, meaning Whisper wasn't trained with SOT. So did you just try training Whisper?
Oh yeah, yes.
Do you have those numbers?
I do, actually.
Okay. I mean, I didn't see them in your, if they were there in your table, I missed them. Because the question would be, is standard SOT, there we go. Let me see for a second.
Yes, so what we did, I tried to, instead of concatenating the embeddings, I tried to like average them or mask average them, or even I tried some weighted sum, but it works only on the artificial mixtures like DB2 mix, but it doesn't work on the not so far.
Okay, then the other thing was that if you really wanted to, well, not really, you want one way to give the decoder the advantage of the multiple looks is not to create 3 copies of the encodings, but to
have just a single one, yeah.
A single one of the same length, but concatenate all 3 embeddings. So make the embedding size 3 times. And then project down or something. The idea being that if I'm going to pay attention to frame numbers 35 to 36, I have 3 looks at those frames, one from each diarization masking.
Yeah,
but they're all in the same place.
Yeah, I think that what they are just suggesting is this weighted sum. So what I did in this weighted sum, I concatenate the embeddings, encoder embeddings across the dimension.
No, but don't sum them, just leave them alone.
Okay, okay,
okay. Yeah, and I was just thinking that there is something a little bit unsatisfying about, like, the way this is not working out, and we should look into it. Actually, go back to
one more thing I would like to try. So Matthew will talk about this this new approach, how we can use actually CTC for multi-talker ASR. Yeah. And the other idea would be to have this multi-talker CTC encoder and use it with this SOT decoder. So that might also work.
Okay, all right. Yeah, I'd still be curious to know what happens, not if you do a sum or average, but just, actually I take that back. When you say concatenation, maybe that's the experiment I'm thinking about. You just concatenate the 3 embeddings, right?
Yeah.
Okay, so that is, sorry, I take that back. That is the one I'm thinking about.
Yes, so as you can see on this.
No, not concatenation in time. Concatenation.
Along the dimension, yes.
Okay. So then that's not the experiment I was thinking. What that does, in my opinion, is that your attention computation is still on size t, not on 3t.
Yes.
And so when it pays attention to a frame, it pays attention to a frame. It just has the option of looking at 3 different looks of the frame. So, okay, all right, thanks.
Okay, well, thank you, Sanjeev. You prefaced this section quite nicely. SOT has a few problems in its current formulation, mostly that the encoder is used 3 times and the alignment is somewhat tricky to get out. And we realized actually that there's a nice generalization of SOT that uses something called shuffles. And just to preempt any questions, when we mean shuffle, it means the riffle shuffle. So take like a deck of cards, split it in half, and do this shuffle. Not right now. Okay. We're going to ignore the speaker attribution part just for a second, and we're just going to focus on the transcription and alignment of overlap speech with shuffles. So as Martin mentioned, serialized output training relies on alignment to determine the best serialization, or any serialization really. So one version was the speaker labeled version. So Emma, how was JSALT? Hey, Emmanuel, it was great. That's one serialization, but perhaps in time it actually looked like this. You might have utterance boundaries and you can serialize it this way instead. So our thought is, well, why are we imposing any particular serialization? Let's just consider all of them and let the model pick the one that it thinks is best. And you know, this could be word level or it could even be a subword level serialization depending on what kinds of tokens you're using. Okay, so just in a nice environment where we can understand what's going on, I want to introduce what SOT is doing, serialized output training, versus this shuffle thing. So we're going to consider CTC for now, because it's well known. For those of you who don't know it, and especially in the context of multi-talker ASR, what does this mean? Well, we might have two transcripts, Y1 and Y2, and some speech X, and CTC tries to label each frame with a token. So that's what this A is. This is a sequence of frame labelings. It might look something like this, for instance, in SOT. So for the transcript, hey Emma, for audio of length 8, we'll label each frame. We get a score for that particular labeling of frames, but many different labelings of frames align to the correct transcript. So the idea in CTC is that we want to marginalize, so sum over all of them. And that's what that Y1 concatenated with Y2 symbol means. So our proposal is very simple. We're going to take this and make one small modification. That. So what does this symbol mean? It means the shuffle product. So this means, it comes from literature and in computation. People use this to model concurrent processes, for instance. If I have two strings and I want to find all shuffles, again, riffle shuffles, that's what that symbol means. So what's an example? Here's the same sequence, hey Emma, for a length 8 sequence. And now we can introduce the M from Emma before we finished hey, and that would be considered a valid shuffle. And that's one shuffle that the model might decide to use. And just in case you haven't gotten it, there's a little animation for you to understand what we're doing. Okay? So this is modeling overlap with serialized outputs. All right, so what does the space of all shuffles look like? Well, for two sentences, and these come from AMI, now these two sentences happen to actually occur one after the other, but in many corpora, we don't necessarily have time boundaries. So I might just have some audio, and I know that both transcripts occur within that time range. So if I assume that they could be completely overlapped, this is the space of all shuffles, and we can code it in a weighted finite state transducer. So on the axis on the top left, you see the first one, and on the top right, you see the second one, and any path through there is a particular shuffle. Okay, the problem is this graph can get quite big, and so if you have more speakers, you get more overlap, the space of all shuffles can be bigger, and if it gets very long, it can also get quite big. So if we do have some timing information, notably if we're training with synthetic data, we always have the start time and duration of the utterances, then we can use some heuristics to state whether certain parts of the sentence are likely to be on their own and not overlapped, and other parts of the sentence we might still consider some overlap. So we can adjust some collar that decides how much overlap we're willing to have or consider that can limit the size of the graph. And in the case of using a small enough collar, in the case where the utterances actually occur completely sequentially, we retrieve the serialized output training sort of serialization. So that is one particular shuffle. So this generalizes the idea. All right. The cool part about this is now that we've framed everything in terms of WFSTs, we have all the normal algorithms that we would use, including, for instance, Viterbi alignment. So the Viterbi best path through a graph, if you take this graph, composed with the CTC graph, it gives you a time alignment of the multi-talker transcript for free. And other algorithms for multi-talker ASR allow for alignment, but it's a little bit cumbersome. And so I was quite happy that now we have, in theory, something that looks like a multi-talker alignment algorithm. So here's one example of an overlap speech example, and it's aligned well.
I don't know North, says Kirkland. Why did you stop me?
Okay, so there were two speakers there, and there was overlap. One person says, oh, Mr. North, and the other person says, I don't know, says Kirkland. Okay. Now, I'm not going into too much detail about it now, but to get scores, to compare it with other models, it was actually very convenient to also try to do the speaker attribution. There's easy ways to do that. You can use a fixed labeling according to speaker start time. We just added an extra branch to the model, and we explored two little ways of doing this. The important part isn't really so much the difference between the two methods, but at least on the Libri2Mix test set, it was actually briefly outperforming DiCal v3, although I think Alex came up with some tricks that may have even surpassed this result. Needless to say, it was quite promising, and I'm happy with the result. So it turns out that overlap speech, it seems, can be modeled with shuffles. We have a one-pass alignment algorithm, promising results in Libri2Mix, and we're going to be extending this to longer form data, more speakers, and more realistic data. Now, there's some other cool things that you can do with FSTs, and my colleague Matthew's going to tell you about them.
Okay, so I'm going to be presenting a quick idea that I had for improving training of diarization systems. And as Matthew alluded to earlier, this is not actually specific for diarization, but kind of any sort of audio segmentation task. So what I mean by that is, let's say we have some kind of recording where someone is speaking, and what we would like to do is simply annotate where the speech is. And this is exactly how the kind of training and evaluation data sets that we would use for this task are going to be annotated. But now the models that we train are kind of trained with a frame level loss. And so the first thing we do is we convert this like segmentation of saying like a start and an end time for an utterance into frame level labels of zeros and ones. But kind of a claim that I'm making is that that may not be the optimal frame level sequence. So like, for example, we often kind of over-annotate around the boundaries of the audio. So maybe you want a 0 at the beginning or the end, and then maybe there's some small pauses within a single utterance, and so it'd be better to have a 0 in those moments as well. And in fact, if you look at a lot of kind of different networks that are trained for these sorts of tasks, if you look at the like trained model predictions on test utterances, you can kind of see this kind of behavior already, where the like likelihoods will drop on individual frames. And as a result, when we deploy systems like this, we tend to use something like a median filter to smooth out these labels and turn it back into a like higher level segmentation that matches the annotation. And so that brings me to kind of the idea behind this approach that I've come up with, which is to try to do something like an inverse median filter on the label sequence. So here you can see I've kind of had a diagram of a state machine that's going between zeros and ones, and we can implement this in saying, and have a state machine that implements like a median filter that says, we can only have a certain number of zeros within a particular window. And so the idea is to then say we can basically re-annotate, in some sense, our training data with these like permuted label sequences. And so then in terms of using this as a loss function, there's kind of two like very easy ways to use it. One is to simply say we're going to compute whichever label sequence produces the lowest loss. That is, most closely matches the network output, and then we're going to backpropagate only from that label sequence. So this is kind of similar to something like permutation invariant training in diarization or separation, where we're saying there's some ambiguity with our labels, and we're just going to only backpropagate to the one that seems to match what our network is doing. And then the other approach is to say we can always just marginalize over all like valid label sequences. And this is going to be very similar to CTC, as Matthew was just talking about. And so unfortunately in our current kind of testing situations for these loss functions, there's a very, very slight underperformance compared to just training with regular binary cross entropy. But unfortunately, the setup that I'm using right now has generally quite good annotation that doesn't have those like sloppy boundaries that you see in a lot of data. So kind of the next step is to try scaling up the setup and using a lot more data, which as a result is going to result in like lower quality data, and hopefully we'll see some benefits then. So next we'll move on to kind of the next kind of chunk of our team. Yeah, sure.
So you were a bit concerned, go back to the previous slide, that you may be working with a data set where the boundaries are too tight and there aren't too many spurious like, basically small silences have not been left in and that edges are pretty tight, right? So could you take that data set and maybe do the reverse, namely pad a little bit of boundaries to the speech regions and merge speech regions which are separated by very little silence and just do it again to see if you recover it?
Yeah, yeah, that's definitely something we can try.
Okay, all right, cool. So I'm understanding the hypothesis correctly, that if that experiment worked, then it would prove that that's what's going on. Okay.
Yeah. So next we'll be talking about the multi-speaker front-end processing, which if you've been kind of paying close attention to our presentation so far, you may remember that we've been kind of trying to eliminate things like a separation component to the system. And so it might seem strange that we're still working on these sorts of things. But one thing to remember is that models like Whisper are not trained on multi-speaker or multi-microphone data. And so there is some kind of like loss of information when we use a model like Whisper on these domains. So one kind of motivation here is to try to utilize some of that information and then kind of shift the input data to something like Whisper can better use. And it still doesn't violate the kind of end-to-end motivation either, because a lot of the systems we're training can then be fine-tuned end-to-end, or even you can learn representations that are then going to be integrated without having to go back into a waveform. So I'm going to talk about the other thing I was working on this summer, which is weekly supervised speech separation. So to very quickly introduce the problem, what is speech separation? One thing to remember is that this is an audio in, audio out task. So we're not doing any sort of labeling here. We are actually taking audio as an input, and then the network is going to be producing audio as the output as well. And so this is the task of dealing with overlapping speech. That is when multiple people are speaking at the same time, and we want to take in these recordings and then produce separate recordings for each talker in that overlapped region. So the equations for this are like very simple, so I'll very quickly run over it. So here we have x of t. This is going to be our mixture or our input to the system. And this is simply a sum over the n s of t signals, which are going to be the speech signals for each of the n speakers in that recording. And then the second equation, g, is going to be our network, so it's going to be taking in the mixture signal x of t and then producing estimates of each of the Sn of t signals. And then to go into how the networks are trained, the way we generally do this is with synthetic data. So what we have is we'll take, for example, 2 clean, non-overlapped recordings of speech, and we're just going to digitally sum them to produce a mixture. This mixture is what is going to be the input to our network, and then the network hopefully is going to estimate those original clean signals before they were mixed together. And since it's synthetic, we do have the ground truth, and it's very easy to then have a loss function that encourages the waveforms to be as close together as possible. And then speech separation systems are also generally quite simple. So kind of in essence, they're encoder-decoder models with an additional component in the middle that splits up intermediate representation. So you can see on the left I have the x of t, which is our input mixture. It goes into the encoder, which then produces a sequence of features. So tau is this like new time dimension, and then d is going to be this dimension of the embeddings. And then on the back end, you're going to have the decoder that takes a similar like sequence of d-dimensional features and then turns it back into an audio sequence. So then the third component is this separator in the middle, which is going to map the like representations of the mixture into representations of the individual speakers. So to move on to kind of the problem that I was really trying to tackle with my proposed work is we'd like to train systems on in-domain data. So kind of the traditional way we do this is with like studio clean speech, which is not going to be representative of like real-world overlap, like some of the recordings you've heard earlier today. So we'd like to use data that actually comes from the like acoustic conditions that we're going to use. which means that the recording is going to have noise in them. So now when we create these synthetic mixtures, we have both like 2 speech signals as well as 2 noise signals. And hopefully we'd be able to still kind of do the same thing and say we want to do an estimate of the 2 speech signals that were added together to produce the mixture. But it gets more complicated because we also have some extra noise there. So we have this noise mixture, and if we were to train this in the same way as that we did in the kind of clean speech setup, we would actually be asking the network to separate the noise signals, which is maybe something that's very difficult to do. So for example, a very common like noise source is something like an air conditioner. And if you could imagine taking 2 recordings of an air conditioner and adding them together and then trying to separate them again, it's pretty much impossible. And then on top of that, even if you can separate things, in this formulation, you're actually saying we need to map the noise sources back to the speech signal that they were originally with, which is something that, you know, is not really a theoretically possible task either. So the approach I was looking into is to say, basically the idea is we're not going to learn to separate, we're going to try to learn separable representations. And this allows us to have to make fewer decisions on things like assigning noise sources to speech signals. And so the idea here is that in a separation network, what I've done is I've taken the linear layer that does the separation and replace it with a matrix multiplication. So it is actually the same operation in the network that I was working with. But rather than using a like learn transform, instead I'm computing kind of an optimal transform. So what the like A matrix is going to be is, since we still have ground truth signals, we can compute this embedding representation for the mixture, the embedding representation for the target source, and then we can actually compute like a least squares solution to say what is the matrix that's going to map from the mixture embedding to the source embedding. And then you can train this whole thing end to end. So now, kind of the tricky part is how to make this useful, because we don't have a like supervised separation network to actually kind of perform the task that we were trying to do in the first place. And so with the formulation on the previous slide, the network trains like very well and converges pretty quickly. But then the question is how to like get separation out of it. So one idea is to just say, well, we can try fine-tuning a linear layer after we've learned the encoder and decoder. But the problem is that the representation space that gets learned is not consistent, so you can't learn a single transform that works for all speech. So then kind of the next idea to try after that is to say, maybe we should have some kind of constraint that encourages these optimal matrix multiplies to all be the same. So then you could use that transform in a like deployment setting. But then unfortunately, this kind of caused the network to not converge at all. So then the third idea I was exploring, which is kind of working to some extent, is to have 2 branches in the like model training. So on one side, you have a like fully supervised branch where we're using synthetic mixtures of studio speech with artificial noise. And then we have this optimal transform on the real data that has this like noise assignment issue. And this model is kind of training to some extent, and I'm still exploring its application on real mixtures. So next I'll be passing it off to Yoshiki.
Okay, so the next I present flexible and versatile speech separation, enhancement, and extraction. So in real-world application, we have multiple microphone arrays, but their configuration, so the number of microphones, the array shape is different in each device. In addition, the number of active speakers is different in each situation. For example, a single speaker is active in this kind of a lecture style, but multiple speakers talk simultaneously in the discussion period. To handle those various conditions, we design a Flex I/O that can handle arbitrary number of the inputs, microphones, and output speakers. Flex I/O inherits array-agnostic processing from the multi-channel diarization presented by Jianyu and Mark. Also, the Alex utilized similar technology to exchange information across speakers in the DICO framework. So in the following slide, I'll recap such kinds of the array agnostic processing or multi-channel, multi-stream communication modules. So first, the transform average concatenate, or TAC, was proposed for multi-channel speech separation. This architecture aggregates channel-wise information, GM, by average pooling after the fully connected layer. And then its processed version is concatenated with the original channel-wide feature. And we usually insert these kinds of the module after the channel-wide spectral or temporal processing modules. Next, cross-channel attention is similar, but it can perform more complex and more dynamic channel communication. Here we consider the sequence of the channel-wide feature. In this case, the sequence length is only 2, but in the case of the 8-channel microphone array, the sequence length will be 8. And compared with TAC, this cross-channel attention can perform input-dependent and channel-wide different aggregation strategy. In addition to this, we also explore co-attention that was originally proposed for multi-channel diarization. Different from TAC and cross-channel attention, the co-attention intervenes channel-wise temporal or spectral processing by attention mechanism. So here, the left figure shows the vanilla channel-wise attention, like it is for the temporal processing or spectral processing. And in the right figure, the co-attention aggregates key and query from each channel and then compute a shared attention matrix. In this case, we don't need additional parameters for channel-wise communication, while TAC or cross-channel attention require additional parameters dedicated to the channel communication. So here are the experimental result of 3 variants of Flex.io and the existing method. So Flex.io outperforms the existing flexible speech enhancement and separation method in terms of SDR. Also, like Flex.io with co-attention improved the word error rate from 6.7% to the 5.1% in chime for real recordings. As another project, we have also explored target speaker extraction. In target speaker extraction, we provide a queue specifying the target speaker and aim to reconstruct the target speaker utterance from a noisy audio mixture. Here we use the target speaker's activity because it can leverage rich annotation in the meeting corpora. But its training has a domain mismatch issue. Real recordings have different characteristics from the simulated dataset in terms of the overlapping pattern or speaking style. And it is not easy to train the target speaker extraction model on the real data due to the lack of the ground truth. So we have explored semi-supervised training for target speaker extraction. In addition to regular supervised training on the simulated dataset, we perform unsupervised training on the real recordings. But here, we don't have a ground truth for target speaker extraction. So we add 2 real recordings, Y and Z. It could have multiple speakers, and then we perform target speaker extraction and train this neural network so that the real recording is recovered by adding corresponding extracted signals. With AMI recording, we have a good initial result, and after the workshop, I will explore more in this direction.
Yeah, before many group mates talks about direction, condition, ASR, direction, sequence, condition, everything. So here I will introduce some derivation, condition, separation, and ASR. Yeah. In real-world conversation, they are not fully overlapped. People usually take turns to speak in meetings or phone calls. It's rare for more than 2 or 3 people to talk at the same time. So Microsoft possessed a method called continuous speech separation. It assumes that at each time window there are maximal 3 speakers speaking, so it can separate the mixture to the 3 streams. Each stream is only 1 speaker. But the problem is at any time only 1 speaker is active per stream, but you don't know in each stream, different windows there are whether the same speaker or other speaker, you don't know who them is. Yeah. So we have proposed a method called direction condition separation, DCFDS. If we get some global speaker dilation results, we first windowed it to some local dilation results like this. You can map global 4 speaker results to the local 3 speaker result. Then you can use this local dilation to condition separation to generate like 3 stream separated audio. But because you know the first speaker dilation you input is the first stream, the second is the second stream, and the local result is concepting to the global speaker ID. So when you do the ASR, like you just input to the visible, you can get some ASR local system or ASR results. And you can use the mapping to recover the global 4 speaker transcription. Yeah. But what I want to do next is if we replace the visible to a more powerful multi-speak ASR, whether we can get some better results. So now I want to explore some direction condition separation and direction condition target speak ASR, like we just use a DICO to do some tests. And you can see when you apply the separation before the DICO, your ASR result, you can decrease the insertion error and the submission error, although the direction error is increased. Maybe the separation separates the target speaker, and you will get more direction error. Yeah. But you know the DICO never sees the separated audio. It just train on some real conversation. So maybe if we try to train the direction condition separation and the DICO, whether we can get better results. But there are lots of problems. Because separation is typically trained on very short window, like 3 seconds, 4 seconds, and 5 seconds. But ASR usually trained on a long window, like visible is trained on 13 seconds. And there are some research show that if you train the ASR train the visible-like system on the short window, you will get worse results. And the supervised separation model are usually trained on simulation data, but ASR is trained on the real data. Is also a gap. So we first explore long window speech separation. We found that if you just extend the window from 3 seconds with the maximal 3 speaker to the 13 seconds with the maximum 4 speaker, you will get a very poor WER result. But if you add some more variant features and modify the conformal article, long window separation approaches short window performance. What we next want to do is we want to use the FDDT, like the DICO, into each into the separation encoder at before each conformal block. Then we can train our system do some target speaker extracting. And then we can load this target speaker extracting system and the DICO weight joint tune with the ASR loss on real data, like this article. This work is just the start from the workshop. Maybe we will complete after the workshop. Yeah, that's all. Yeah.
Keep going back, yeah.
Yeah.
Keep going back all the way to Matthew's slides.
Yeah, this?
No, Matthew's slides, Maciejewski. The one with the cartoons.
What?
Keep going back.
Which one?
Yeah, stop. Forward. One more.
One more?
Go forward. Stop. Yeah, this is good.
Yeah.
So, Matthew, I have a suggestion. The green boxes, the people in there, you should draw them wearing some hats, because those are S hat.
That's all. They will definitely help to solve the whole problem. How do I switch slides? So that takes us to the conclusion. So I should make some last conclusive remarks. I have prepared infinite amount of conclusion slides so that I can fill up the rest of the time. So whenever Sanjeev thinks that the time's up, he will stop me, and that will be it. Okay, time's up. At least something. Okay. So this will be just a quick recapitulation of what we have done during the workshop, and what maybe some highlights. Maybe you should take it that they are maybe even my personal highlights, because I was preparing these slides and somebody else would highlight other things. But anyway, one of the things that I would like to really highlight is that we prepared this leaderboard and basically this new benchmark, which we try to share with everybody, and everybody can now submit their own results into the leaderboard, and we hope that this will be and we have already some state-of-the-art results in the leaderboard, so we hope that this will be something that will drive the field, and people will start using it as a really benchmark for multi-talker ASR. You can find through the QR code where the leaderboard is. I guess you can find it in the slides once you download them. You have heard a lot about this DICO model, which was kind of the centerpiece of this workshop. So the model was something that us, BUT and JHU, we had a joint submission for Chime 8 challenge. So that is already about 1 year old, but then we have been working on it in the preparation for the workshop and throughout the workshop, and we have improved the model quite a bit. So at the moment, we feel that it is something that also provides state-of-the-art results, and it's a relatively lightweight, simple system which already provides very competitive results, and again, it should be accessible, so you can download it. We have a demo, which if somebody is interested or we have time, then maybe Dominic or Alex can show you how the whole system works, record something for multiple people, and see how it transcribes multiple people talking simultaneously. Then continuing on the DICO, so it's not just that we brought this model and we improved the model, but this model, as I said, it was the centerpiece of many things. We have used the model for extensively throughout the workshop for various extensions and interactions with other subsystems. So there's a list of what the model was involved in. So one of the things that Alex was talking about, making it a truly multi-talker ASR system through adding some communication between the individual instances of DICO, that they would communicate with each other. Then he added this conditioning on additional enrollment, so you can provide more speech of the same speaker and condition it on it, and it also improves. Jean was showing you the Bayesian extension, so he treated these transformations that were added to the DICO model to deal with to basically incorporate this diarization information in it. So he was training it using Bayesian learning. You have heard about the heat heuristic, which was brought to simplify or to make the decoding more efficient and more streamlined. So the heat heuristic, if you remember, was rather than decoding, if there are 5 speakers in the utterance, decoding all 5 speakers, we would just be decoding maybe only 2 speakers, and we decode multiple speakers only if their speech overlaps and we cannot decode them at the same time. It was the extension of the CLSP output training. Martin Kotzor was presenting it, and other things. The work in preparation would be jointly trained diarization conditioned source separation, and also there was a plan to use it. It served as basically as for evaluating the synthesized speech that you have seen here, also as a backend for evaluating different techniques. Also, this DICO was maybe inspiration for different things. So one thing was Dominic basically now made this DICOP, which is the same idea as DICO, but based on Parakeet, which is now can be used for long-form decoding. It is about 20 times faster than Whisper. Large that is used in DICO can decode hours of speech eventually. Well, up to 30 minutes is what Dominic says here. And then the idea of conditioning ASR on diarization was also extended to other tasks. So now Prachi is using diarization conditioning for training embedding extractor or fine-tuning embedding extractor so they can robustly handle overlap speech. It's going to be used, or it's used in target speaker extraction, which was work by Yoshiki. Then we have this is also Yoshiki multi-input, multi-output joint speech separation with weakly supervised adaptation to real-world domain, multi-talker speech synthesis. So this is eventually was idea that even the speech synthesis can be diarization conditioned. So I guess this is also something that will come next. And then, so this would be about DICO and what role it played in the whole project. Similarly, we brought our diarization system, which is this diarization system, which is again provides state-of-the-art performance on many diarization data sets. But here we try to, and we successfully extended it also for multi-channel diarization. So we saw the improved results, and was done either by using the this microphone array agnostic attention mechanism, where again instances of here WAFL and pre-processing were communicating each with other, where the individual WAFLMs processing individual microphones were communicating with each with other, or through the integrations of the GCC-based spatial features that Mark was presenting. And also this diarization is also used as a component and in other systems. Prachi is using it for her graph neural network-based clustering. There is a plan to train joint diarization, source separation, and ASR in single stack. We have used it for these different diarization conditioning problems. Okay, so these were the tools that we brought. now the problems that we were trying to solve. So we were considering, shall we do ASR conditioned on diarization? This is what DICO does, but we also explored the opposite things where we have diarization conditioned on ASR. So this is the work that Emre was working on, but also people from USTC, Royu was presenting it here. So the idea that you have, you basically first decode individual sentences, and from the sentences we extract speaker embeddings, but also some embeddings that comes from large language models, and those are concatenated and used to cluster, to identify speakers, to cluster speakers. Another idea which I think is interesting is actually here I want to talk about the different strategies that we used for the multi-talk ASR decoding. So what I just said, shall we do first diarization or ASR? So we saw it on the previous slide, but even if we do maybe diarization condition decoding, in which order should we decode things? DICO basically runs this target speaker ASR individually in terms for each different speaker, but Martin Kotzor presented this work on serialized output training, where there is a single decoder that in single run decodes all the speakers, but then the question whether it should decode things again speaker by speaker, first one speaker, then second speaker, or whether it should interleave individual speakers. So we had some interesting results with that, but maybe to me at least, the most interesting thing was this new framework based on this shuffled automata that Matthew was presenting, which allows flexible on-the-fly shuffling of words across speakers, and it actually doesn't even need to be conditioned on diarization. So if we are asking diarization first or second, maybe not at all. So it can be done automatically. Well, serialized output training can eventually do also implicitly diarization. But here, again, maybe we don't need diarization at all, and maybe we can do that together with ASR. And I see that I'm saying twice the same thing. I don't know why. And this technique is showing promising results. It was easy to implement thanks to K2, so that just thank you, Dan, for making us this tool. And then maybe, to me, maybe this is the most principled approach to multi-talker ASR. We have some promising results, so let's see where this goes. And there were some new metrics proposed for evaluating diarization. So Royu was presenting this new diarization word error rate, which seems to correlate much better with the actual ASR when this diarization is used for diarization conditioned ASR, or well, in any way for multi-talker ASR. So maybe this is something that people should adopt. And then another thing that I would like to point out was that there would be certain mechanisms that people have used, and they have shared ideas about those, and they have shared their experience. One of those was this communication between channels. So it was a mechanism that was actually used for many different things. Alex at the beginning was presenting this communication where he would run different instances of Whisper, and he would let them communicate each with other. And I see that while copying this picture, I actually didn't copy exactly the component which shows how they communicate. So there was one thing, but the similar mechanism was presented for multi-channel diarization, so that the communication, the same kind of communication was also between instances of not decode, or not well, there was also encoder in DICO, but here it was not for decoding different speakers, but actually for taking input from different microphones. Joshiki is basically working on similar things, but for source separation, for speech enhancement, and he was presenting these different approaches. But then the same idea was eventually used for speech synthesis, where they will be running in parallel different speech synthesizers, synthesizing different speakers, and they would communicate each with other also through the similar style of communication. And just to say, the name of the whole team was this end-to-end multi-channel, multi-talker ASR, but we didn't eventually work only on multi-talker ASR. We also worked on different related challenges. So of course, diarization, which was eventually input to the multi-talk ASR, but it is technology on its own. Speech enhancement, target speaker separation, conversational speech synthesis. Dominic was working on different transformer architectures for long-form decoding. Drashan proposed these novel adaptive chunking methods, which again can be used for in general for ASR or in general actually for any speech or not even speech task that uses transformers. So it's a very general method. And okay, so this brings us really to the end. So I'm asking this question: are we there yet? I mean, regarding this, the topic of our theme, which was end-to-end multi-channel, multi-talk ASR. Well, we improved our multi-talk ASR solution to be relatively simple and highly competitive. But actually, we didn't even address this multi-channel aspect of ASR. We did it for diarization, but we didn't do that for ASR. So maybe we should scratch this M here in the title, and you can see that Emma is not that happy anymore. Well, as it looks like Emmanuel still doesn't care. But, okay, so we didn't address this multi-channel, but we did it for diarization. Perhaps we can reuse the same components now hopefully we can reuse the same components for ASR, and it would work the same good. Well, we didn't yet manage to train the system in end-to-end fashion, so maybe we should scratch also these others, which maybe we should rename our team to just Ma instead of Emma. Now even Emmanuel is not that happy anymore, but well, I'm not that stressed about it, because again, we actually worked on several promising strategies how to deal with the end-to-end training. Dominic is trying to train models which allow long-form decoding. I think that this shuffling strategy is something also that can allow us to easily backpropagate to the whole system, build end-to-end systems. There were other ideas how we can build a complete end-to-end systems. So I think that we have prepared many key ingredients during this workshop, and now just we need to keep cooking and brewing the ASR fuel. And
precise temperature of your coffee.
You have to ask ChatGPT, because ChatGPT generated this picture. Okay, so, but I guess that those of us that drink coffee knows what fuels us when working on ASR. So we need to pour more coffee into ASR. Okay, and now I don't want this thing to sound pessimistic that we failed at the workshop. I think that actually we did a lot of work which on its own is already very valuable, and we have a very, very good result, very interesting result. So that's I thought that I would be a little joking at the end. But at the same time, I know that as Sanjeev says, that the most important things usually happens not during the workshop. Well, the important things happens during the workshop, because the important things during the workshop is that people meet here, they make contacts, they brainstorm, they start working on some ideas, but many of the ideas are eventually realized only after the workshop. And this is why I'm wearing today this T-shirt, which is the T-shirt from the not JSALT, but the John Hopkins Summer Workshop. It was how it was called. Still in 2008, which is where I was leading the team of working on this is JFA's joint factor analysis, but this eventually evolved into I vectors, which were, I think, the first speech embeddings that were actually for long times was the state-of-the-art methods for speaker recognition. So, and that also happened only after the workshop. During the workshop, we just explored that something like that is possible, but we didn't call it I vectors yet. Okay. So then this is the end, or as I said, the important things happens after the workshop, so maybe better we should say to be continued after the workshop. Thank you. So I guess that we can now answer any questions if anybody has. I was measuring the time that we burned on Sanjeev's and Honza's questions already during the, and it was 15 minutes already, so we can subtract that. And
thank you. Great presentations all over the place. I have one question related to actually Parakeet and Whisper. Whisper is a weird model in the sense that it does not just do speech recognition. So replacing Whisper with a different model to improve speech recognition, is that basically taking away some of the functionality that Whisper offers and make it more targeted?
It's definitely taking some of the functionality, for example, some of the functionality. So Whisper, we used it just for speech recognition, but we, for example, know that when we fine-tune it on English data, it was very well performing also on other languages. Parakeet on its own is trained also on multiple languages, but it's only English, this one. So this you don't have multilingual. There are some models from NVIDIA which are multilingual, but this particular is not. So you lose, for example, multilinguality. We didn't try. I guess that we could try to use we never tried that, to use it for speech translation, even this multi-talker speech translation. Possibly it would work. We could try to do that, just to switch. We have to do that, to switch the talk into another language and speak to it, a multi-talker in one language, and let's see what speech translation functionality it keeps. So most likely it does. We never tested it, and of course you don't get it with Parakeet. Yes.
Yeah, actually, I'm not sure if these other functionalities are that useful, quite honestly.
Well, yeah. No, but that's what Whisper can do other than Parakeet, yes. Yeah. And I just ask people from our team, if you have the answer, just let me know and I will run to you with the microphone.
So let me ask a slightly provocative question. At what stage do you think some of these audio language models might answer your questions? Of course, they will have much more training cost and so on compared to whatever you're doing, but still.
So they would do that automatically on their own, and we don't have to build this system. Yeah. Well, I guess that in a couple of weeks, but the thing is also maybe it will do that at some point. Also, it's not just training cost. I guess it's mostly would be the processing cost. And well, no, is there any acoustic language model that is trained, for example, on multi-channel data on multiple microphones? I don't know. Maybe yes, because maybe it already actually gets stereo recordings. I don't know how Google currently deal with.
Yeah, I was about to say that the best I would expect is stereo, because otherwise things would become dependent on the number of channels, and there's no easy way to accommodate variable numbers.
So I guess that the work that we do is still relevant, even if large language model, large audio models takes over.
Other questions? So I have a comment, Lukas. You said this is probably not, I can't remember who said it. This is not the end. This is not even the beginning of the end. Perhaps it is the end of the beginning. So yes, this will continue. Okay, if there are no more questions, let's thank the team again.
Thank you.
Does everyone want to come down and have a picture? Like all team members come down here and we'll take a picture.
And while coming, of course, I would also like to thank to all the organizers and maybe mention if the external contributors like Pianote providing transcription for data, and we collaborated with people from NTT, Mark Decroix and his student, and so there were some things that even didn't show up in this presentation that were actually very fruitful for the workshop. What? Which one?